how does AI truly learn about the world around it? I mean, not just recognizing pictures like a cat or whatever, but really getting how things work. How does it go from seeing patterns to, actually understanding and acting in our physical world?
Yeah, it's a huge question.
Right. So today we're doing a deep dive into some really interesting research. It's from Meta and the Quebec AI Institute about something called V-JEPA 2. And this isn't just about like making AI smarter in the abstract.
No, not at all.
It's about giving it a much deeper, almost intuitive grasp of reality. And then this is the really cool part, enabling robots to use that understanding to actually do things in our world.
Exactly. That's the core challenge they're tackling here, bridging that gap between watching the world and interacting with it.
Yeah.
How does an AI learn robustly just by observation and then, apply that knowledge to achieve goals?
Right.
In this paper, it introduces a really fascinating self-supervised approach. They combine just enormous amounts of internet video with actually a surprisingly small bit of real-world robot data. And the goal is to build models that can understand, predict, and even plan physical actions. It's sort of a leap towards a truly well-informed AI, one that doesn't need constant hand-holding with labels or specific training for every new task.
Okay, let's break that down. You mentioned self-supervised learning. How does V-JEPA actually learn from all those YouTube videos or whatever without labels telling it, this is a person opening a door, or that's a ball rolling? How does it figure out what matters?
Good question. So this is where the GP architecture comes in joint embedding predictive architecture. That's the core engine, really, of VGB2. Now, unlike a lot of models that try to, say, perfectly regenerate every single pixel in the next frame of a video.
Which sounds incredibly hard.
It is, and super computationally expensive. GP does something different. It learns by predicting masked parts of the video. But crucially, it does this prediction in a sort of abstract space, a learned representation space.
Okay, learned representation space. Can you unpack that a bit, like an analogy maybe?
Sure. Think of it like learning the meaning of a scene rather than just the surface appearance. Imagine you take a video and you blank out a section.
Yeah.
Instead of trying to repaint every blade of grass or every reflection perfectly in that blank spot, which might be unpredictable anyway, GPO focuses on predicting the higher level, more predictable information. Things like, where is that ball likely to be next? How is that hand likely to move? What's the overall dynamic?
So it's not sweating the small stuff, the unpredictable details.
Exactly. It's trying to capture the underlying structure, the semantics or the physics of the scene in this abstract representation. And that is way more efficient for learning from just tons and tons of messy, unlabeled internet video. It learns the important relationships and dynamics.
Right, focusing on the core action or movement, not necessarily the background noise. That makes sense for efficiency. So how much data are we talking about? You said enormous.
We are talking internet scale, truly. VGPO 2 was pre-trained on over 1 million hours of public internet video.
1 million hours.
Yeah, plus 1 million static images as well. It's just a staggering amount of passive observation.
Wow. Okay, so it watches the equivalent of over a century of video. What foundational understanding did it get just from that? This is before any robot stuff, right?
Correct. This is the action-free pre-training. And it led to some really strong results on general visual understanding tasks, even without any labels.
Like what? What could it do?
Well, for instance, it got really good at motion understanding. There's a benchmark called something V2, which is all about understanding human actions.
Like pushing something left or opening a box.
Exactly, those kinds of things.
Yeah.
And VGPO 2 achieved 77.3% top one accuracy there, which is quite high. It showed it could really grasp complex movements.
Oh, okay.
And it also showed state-of-the-art results on human action anticipation. So, predicting what someone's about to do next in a video. On a kitchen data set, Epic Kitchens 100, it got 39.7% recall at 5. Basically, it's surprisingly good at guessing the near future based on visual cues.
Predicting the future, even a little bit, is pretty impressive. But here's something that really jumped out at me. They mention aligning this VGP2 model with a large language model, an LLM, after all this video training. What does that step unlock? Why is that important?
Yes, this is fascinating because remember, V-JEPA 2 learned purely from pixels, right? No text involved in its pre-training.
Right, no language.
But after they aligned it with an LLM, basically connecting its visual understanding to language capabilities, it suddenly achieved state-of-the-art results on several video question answering benchmarks. We're talking things like perception tests, getting 84.0%, and Temp Compass, 76.9% at the 8 billion parameter scale.
So even though it didn't learn from language, its visual knowledge was so good it could be used for language tasks like answering questions about a video.
Exactly.
Yeah.
It means the visual representations it learned were rich and meaningful enough to be translated into answering complex questions. It's like it built this deep, intuitive visual common sense, and LLM just gave it the ability to talk about it. The researchers point out this is actually a first, using a video encoder trained this self-supervised way for video QA. It shows how versatile that foundational knowledge is.
That's incredible for understanding. But okay, let's get to the action part.
Right.
How does this translate to robots actually doing things, like picking up a cup?
Right. That's the second stage. That's where V-JEPA comes in. The AC is for action conditioned.
Got it.
So they took the pre-trained VG2, the one with all that world knowledge from videos, and they essentially froze its core video encoder. They kept that knowledge intact.
Okay, so preserving the visual understanding.
Yes. Then they post-trained it or fine-tuned it using a relatively tiny amount of robot interaction data. Less than 62 hours of video from a dataset called Droid.
Wait, only 62 hours after 1,000,000 hours of pre-training?
Exactly. And critically, this robot data was unlabeled. The AI just watched the robot move around, watched its gripper interact with objects, but without explicit instructions like pick up the red block.
So it just observed the robot's actions and the consequences.
Precisely. It learned to predict future video frames based on the robot's own actions, its motor commands, and its end effector state, like the position and openness of its gripper.
So it's building an internal model, like if I send this command to my arm, the world will probably look like this next. Almost like imagining the immediate future based on its own potential actions.
That's a great way to put it. It's learning a predictive world model conditioned on its own actions.
Okay. And the paper mentions zero-shot deployment. Now, that term gets thrown around a lot. What does it actually mean here, and why should you, the listener, care about it?
Yeah, zero shot is a really big deal here, and it touches on the practical usefulness. It means they took this trained V-JEPA-2AC model.
The one trained on the Droid dataset videos.
Right. And they deployed it directly onto real Franca robot arms located in 2 completely different labs. Labs the model had never seen data from before.
Never seen before. At all.
Nope. No data collection in those specific labs, no task-specific fine-tuning, no reward functions designed for those environments, and yet
It just worked.
it could perform manipulation tasks, things like picking and placing objects, just by being given a goal image like, make the scene look like this picture where the cup is over there.
Wow. Okay, that is impressive. That really speaks to the generalization of the learning, doesn't it? Taking knowledge from one context and applying it cold to another.
It's huge for generalization. Think about deploying robots in new factories or homes or even unpredictable environments. If they can adapt zero shot without needing weeks of retraining for every new location or slight variation,
Yeah.
that changes the game for practical robotics.
Absolutely. So how does the planning actually work then? How does it figure out the sequence of moves to get from the current state to that goal image?
It uses a method based on minimizing something called a goal-conditioned energy function. It sounds complex, but the idea is fairly intuitive.
Okay, cry me.
You give it the goal image, right? The desired outcome. The model then basically imagines potential short sequences of actions it could take. For each sequence, it predicts what the world would look like visually at the end.
Using that action condition prediction we talked about.
Exactly. Then it compares its predicted outcomes to the goal image and calculates an energy or a cost. How different is my predicted future from the goal? It chooses the action sequence with the lowest energy, the one that it predicts will get it closest to the goal.
And it just takes that one step.
Takes that first action, observes the actual new state of the world, and then repeats the whole process. Plan a short sequence, predict, compare to goal, choose best action, execute, observe, repeat. It's constantly replanning based on real feedback.
A continuous loop. Okay. And how did this VJ2AC stack up against other ways of controlling robots? Was it actually better in practice?
It performed extremely well, yes. Compared to strong baselines like Octo and Cosmos, VGA2AC achieved the highest success rates across the board. On the manipulation tasks, they tested grasping things, reaching for objects, pick and place.
Can you give an example, like the cup task?
Yeah, for pick and place with a cup, VGA2AC hit an 80% success rate. The Octo baseline, for comparison, only managed 20% on that same task.
80 versus 20%. That's a massive difference in reliability.
It really is. But maybe just as important, maybe even more so for real-world use, was the speed.
How fast could it plan?
V-JEPA2AC needed only about 16 seconds per action for its planning loop.
Okay, 16 seconds. How does that compare?
Well, Cosmos, another advanced model they compared against, took around 4 minutes per action.
16 seconds versus 4 minutes.
Yeah. That's the difference between a robot that can operate fluidly and one that feels incredibly slow and possibly impractical for many tasks. That speed up makes real-world deployment much, much more feasible.
No kidding. Okay, so let's zoom out. What's the big picture here? We have an AI that learns this rich world understanding from, like, watching YouTube, and then applies it to control a robot arm with pretty minimal robot-specific data and does it effectively and quickly. What are the main takeaways for us?
I think the core insight is really the power of this self-supervised approach for building these foundational world models. By learning to predict the predictable parts of video, V-JEPA2 builds these really powerful general-purpose representations.
Representations that work for different things.
Exactly. They're versatile. Good enough for high-level stuff like understanding video and answering questions, but also detailed enough for low-level control, like figuring out the precise movements to pick up an object. It's genuinely bridging that gap between perception and action. That's a huge step towards more general AI agents.
It sounds incredibly promising. But like any research, it can't be perfect yet. Did they mention any limitations? Where does this approach still struggle?
Oh, absolutely. They were clear about the limitations. One challenge they noted is sensitivity to camera positioning,
How so?
because the model figures out how its actions relate to the world implicitly from the visual input. Doesn't get explicit camera coordinates if the camera view changes dramatically, or if the robot's base isn't clearly visible, its internal model can get confused. Its predictions about action outcomes might become less accurate.
Okay. So it needs a reasonably consistent view of itself and the workspace.
Sort of, yeah. Or at least significant changes can throw it off. Making it more robust to different camera views is definitely an area for future work, maybe incorporating other sensors or more explicit geometry. And the other big one is long horizon planning.
Right, doing tasks that involve many steps. Why is that hard?
Two main reasons. First, prediction errors tend to add up over time. If you're trying to predict 20 steps ahead, small errors in each step can compound into a wildly inaccurate final prediction.
Makes sense.
Second, the sheer number of possible action sequences just explodes exponentially as you try to plan further into the future. The search space becomes massive.
So asking it to, say, make breakfast would be way too complex right now.
Exactly. That involves finding ingredients, opening things, maybe using appliances, lots of sequential steps. V-JEPA2AC is great at short-term planning, like the individual pick and place, but chaining many such actions together reliably for a complex goal is still a major hurdle.
So what's the path forward there?
Future work will likely need things like hierarchical planning, breaking down big goals into smaller sub-goals, or maybe different levels of abstraction in the model, and of course just scaling up. They mentioned potentially going to 20 billion parameters or more, seeing if sheer scale helps overcome some of these issues.
It really paints a fascinating picture, though, this idea of an AI learning the sort of common sense physics of our world, not just from careful lab experiments, but for the wild, messy data of billions of online videos. It's like learning by watching life unfold.
It really is. And this research strongly suggests that this kind of broad observational learning, maybe topped up with a bit of targeted real-world interaction, could be the key to unlocking truly general-purpose AI agents. Agents that can actually adapt and plan and act effectively in the kinds of complex, unstructured environments we live in.
So for you, our listener, here's something to chew on. If AI can develop such a surprisingly rich understanding of our physical world just by watching countless hours of video, what does that imply about all the other knowledge that's embedded in the vast digital footprint of human activity? All the text, the images, the interactions. What other kinds of understanding could AI unlock from that data, and how might that transform our lives in ways we maybe haven't even imagined yet?